This is a dramatic reading of Sexy Standard Model Symmetries by the Standard Physicist, available at science2.0.com. What is sexy? Sexy is in the eye of the beholder. And the eye actually does dominate, using roughly 40% of our own CPU. We don't ask movie stars to understand spread spectrum communications technology, unless they happen to be Hedy Lamarr. Now, DNA, that's a sexy molecule. It has all those curves. You walk into any new biology building and you're bound to see some double helix motif in the artwork. DNA is directly involved in sex. Human sperm is a collection of 6 billion bases of DNA, 2 energy sources, a motor, and the tools to break into an egg, so long it's the one that's there first. The Standard Model, that is not sexy. Walk into centers of theoretical physics, and you will see these big blackboards and tasteful furniture, a few coffee machines, and pictures of previous pioneers in physics who gained their stature due to the elegance of their contributions. In the year-long relativistic quantum mechanics class I took at Harvard University, the Standard Model was mentioned one time. And the professor was most disdainful, treating the Standard Model like an ugly date. He didn't want anyone to see him with a Standard Model, which is this arbitrary collection of 3 groups. Successful, yes, but The visuals we have of the Standard Model are dull. The group U1 is a circle in the complex plane. I considered including one, but why bother? I mean, should I date Dull Girl? Maybe I should date that redhead who, when she's off her meds, well, she was arrested for lewd behavior in public. Well, you know, it turns out that dull girls just don't get any respect. And the Standard Model is missing visuals. The group of unit quaternions, SU2, should be viewable since it is only 3 numbers that are needed for its Lie algebra. Now, people say this is just the surface of a 4-sphere without showing you what a 4-sphere is. Some might speculate that we can never see SU3 since that requires 8 independent generators. Well, requiring 8 independent generators is not the same thing as requiring 8 spatial dimensions, which we can't see. In this blog, I'm going to animate the continuous symmetries U1, SU2, U1 cross SU2, and SU3. Well, at least almost. I can do that because I have a tool to animate any algebraic expression made out of quaternions. And since I'm a biologist, I use C and Perl as programming languages because C is fast and Perl can stick this with that. I mean, think about, you know, why not put a duckbill at the end of a platypus? Apparently that happened in Australia, you know, a few tens of millions of years ago. The interface chosen was the one that's actually the only one that's lasted since the 70s. That would be the command line. So you go something like Q add, and you write 4 numbers, another 4 numbers, hit the return key, and out pops 4 other numbers. And I've got about 90 simple programs, and I can pipe them together, and easily generate, thousands, sometimes tens of thousands of quaternions. But then how does one create a 4D image? I mean, is that possible? No. The question shows that one is thinking about 4D as 3D plus another D. Well, we don't live in 4 spatial dimensions. Special relativity taught us that we live in 3 spatial dimensions, or maybe I should do it this way, and time. What's going on my watch here, okay? That's a scalar, all right? Now, what I can do is generate analytic animations. All this is an update of René Descartes' analytic geometry. And if you give René a polynomial expression, he can give you a graph. You give me the same polynomial, I can give you a short film. So I found that my visual memory was like so bad that the animations didn't end up making any sense. I had to surround it, the moving picture, with a few other static ones. So I'm going to start off dead simple with quaternion addition. This is one of the few analytical animations I imagined right. Simple quaternion addition is directly related to a deep idea of special relativity, the inertial observer. I am just too much of a minimalist. For this blog, I actually added back some labels. The up, the near, the right, animations, all states, and one state. This almost makes these self-explanatory. The animation is front and center. On the left are 3 complex planes, up, down, and time, near, far, and time, left, right, and time. In the upper right is all states, every state the system goes through during the animation. That was inspired actually by the wave function of quantum mechanics. Below that is one state, a random sampling from all states. And that was inspired by the collapse of the wave function. Now the animation loops, or I have set periodic boundary conditions if you choose to be technical about it. Really, I actually just often need to see the darn thing many times before I can see all that is going on. The basics of trigonometry are the circle and the triangle. Animating these objects seems strange. Look at how straight a line they make in space. But that's how it goes. The circle and the triangle are about space and time, not space and space. We have all drawn circles and triangles in space and space since a young age. Now we can animate a right triangle by bringing our hands together and letting one go off at a nice steady pace until it gets to the edge and then boom, collapses. That was supposed to be instantaneous. This hand wasn't supposed to move like at all, okay? Okay, so it wasn't a perfect right triangle in space and time. Now a circle, I got nothing. They fly apart and they slow down and then they come together really quickly. Now, I'm not sure if that was really a good circle. I'm sure it's an acquired skill, but that's kind of like drawing a circle in space. I mean, you didn't get that the first time. So hopefully that was somewhat accurate. All right, those are the basics. So the abelian group U1 has already been done. It's a circle, and it's created by normalizing quaternion, like so. And you see, actually, I've got it crossed out. That's because I had a discussion with a fellow over at Science 2.0, and he pointed out that a normalized quaternion really has 3 degrees of freedom. Now, so that one below it is more accurate, you've got to really zero out 2 of those degrees of freedom before you have an accurate representation, and then you'll get a nice perfect circle instead of an ellipse in one plane, and you'll have some zeros going on in the other 2. Okay, so please don't rush to comment that quaternions don't commute. The quaternion 1, 2, 3, 4 actually does commute with itself, as does the quaternion. I suppose I should be using 1, 2, 0, 0. That's what I should be talking about, because that really is a complex number in any way you can test it. And that's really all we're asking to do here. And we can take this one quaternion and we can normalize it and square it and do that 1,000 times. The group SU2 is known as the unit quaternions. One way to represent it is with this expression right here. Boom. We've got an exponential going on there. Okay. And then, it's like, are we sure that's going to have a normal 1? And it's like, yeah, if you think about this, this is like e to the I, where I happens to be a 3 vector. So you go e to the I times e to the minus I, that's e to the 0, which is 1. So this thing definitely has a normal 1. It definitely depends on 3 things. So this is a valid representation of the group SU2. So let's take a look at the animation. And that should look so similar to U1. You might wonder, are they really identical? Well, time actually makes this situation kind of subtle. When do things start happening in time for U1 versus SU2? For U1, that can start anywhere, from -1 to +1. And you can look at 50,000 events, and you can kind of normalize these, and you make this animation, and everything's kind of nice and uniform. The same cannot be said for SU2. There's like nothing here, and then there's something like 8 points that grow into a sphere, then shrink back to nothing. It's like Mrs. Pac-Man on mushrooms. Think of the Taylor series for an exponential. If the exponent is super tiny, then this is 1 minus a correction. As long as the 3 vector is tiny, it will huddle around the spatial origin at time equals 1. The only way to fight the world domination of time is for the 3 spacemen to join forces with all positive and negative combinations of 1. So you can start out with 0, the exponential, the quaternion exponential of 0, 1, 1, 1, or 0, 1, 1, minus 1, and basically all those permutations. And then that grows from those points together to form some kind of maximum, and I bet it's a good little math problem to figure out exactly what that maximum is. I just haven't done that myself. Okay, so let me tell you 3 stories about Mrs. Pac-Man, the animation. This animation was actually the reason I bought an iPod. I wanted to carry this insight around with me. It was fun, it was pretty, it was interesting, it was like a good date, and I wanted to show it off. I went into the Apple store, where all those people are super cool, and I decided, well, this is a sophisticated question, I'll go to the Genius Bar, and they told me to just go talk to a sales monkey. And that person was actually very helpful. We got it off this little handheld thing, a little USB stick I had, got it on the machine, and it really looked nice. And I explained to him what it was all about, and he asked for my business card. Now, Sheldon Glashow won a Nobel Prize for his contributions to electroweak theory. He works at BU, and he was giving a talk at a local university. So I emailed him ahead of time to say that I had this animation of SU2, and I would like to show it to him after his talk. And he did his thing, and I walked up with my PowerBook, and it was all turned on, and Miss Pac-Man was doing her, create and destroy kind of dance. And I asked him if he wanted to see the animation, and he declined. I guess he has been approached by too many fringe physicists in his time. Now, the third story is a confession. And now, I admit that I have said in many places that this Miss Pac-Man is a visual representation of the group SU2. I mean, that's what I was going to tell a Nobel Prize winner, but it is not. The simple circle animation is a representation of SU2. I was driven by this hope that SU2 would not be a dull girl. I know I found that that first one, the simple circle, but it looked too simple. Tossing in random numbers into an exponential looked wild. Once I come up with a good way to describe the relationship between the crazy Miss Pac-Man and the SU2 group, I will have to put in correction in quite a few places. But at least now I'll be more right than I was before. So on to Glashow's area of expertise, what U1 cross SU2 really looks like. I probably don't even have to show it, do I? It should look like the other ones. It's a circle. And you can do it algebraically. Let's see, I got it right here. There we go. Okay, so, and really, there's not much to this. When you do that, what is the first time point of this? They actually cluster around -1, and that's because you've got a U1 multiplied by that thing that has a bias towards +1, and that product then throws everything kind of with a bias towards the minus. It can get to every point, unlike the representation of SU2. So it definitely is different in a way, a subtle way, which I think is actually kind of cool. Now, I spent over a year puzzling over how I might represent the group SU3 using just quaternions. Its Lie algebra has 8 generators, and that sounds a lot like 4 plus 4. So you can actually multiply 2 electroweak symmetries together, and that will generate another member of electroweak symmetry group. Because that's how groups work. This was kind of like a P under the mattress problem, something that would bug me from time to time, that I would revisit every once in a while and just wait for the right answer to appear. And what I figured out to do was to kind of change the multiplication table. And really all you need to do is take a conjugate operator and like so. Okay, you see you're taking the conjugate of that first electroweak group and then multiplying it by the other one. And I basically say that's almost SU3. Why almost? Well, because I really do need that conjugate thing. I'm not sure that the multiplication is going to be associative anymore. And group is associative, ergo the representation is a failure. So that's really why I put in the approximation sign. So this is almost the group SU3, except it's not associative. So let us continue our investigation. I'm actually not sure I should show you the image of SU3. I mean, one expects dull girl to be dull. I mean, that is all you've seen so far. I don't work for the Harvard professors with great disdain for the Standard Model. Instead, I've worked with a dull type of number for like more than a decade. I did go to the second meeting on quaternionic structures in mathematics and physics in Rome in 1999, but the third meeting just didn't happen 5 years later. There was that little interest. I mean, I was looking to find it. I wanted to go. Oh, now, ever since I bought quaternions.com, I hear from very sincere folks that I should really drop the focus on dull girl and do calculations with a more popular type of number. You know, do you ever wonder like why I stayed so faithful to dull girl? Well, that's actually just a decoy, because there is no dull girl here. There is only a fascinating woman. It sometimes takes me years to figure out how to ask her a question. And every time I have been rewarded with wonderful insights. If I have to be the only one hanging out with this woman who is so much more than a one-trick pony to do 3D rotations, hey, that's fine with me. I mean, I've got the data that says Nobel Prize winners just don't care about her, which is great. That means more FaceTime with me, all right? So here is the quaternion representation animation of the group SU3. This has got curves, it's got cleavage, it's got grace. The Standard Model is sexy. What happens if the same quaternion is fed into the SU3 symmetry as defined above? Well, this is what happens when you feed 1,000 points in. Oh, you just get unity. This lady is sophisticated. The software is available for download. Go to sourceforge.net, look for quaternions, command line quaternions, and I recommend using the Git repository. That's the way to get the most recent stuff. So here's my snarky puzzle. Imagine a space-time wire cube. No, don't. That's too hard. Do something simpler. All right. Draw a square in the 3 complex planes. Now imagine animating that. Now, got a picture in your head? Good. So go and Google for 4D wire cube and be honest if your imagination matched reality. Thank you very much.